All right. Welcome to the second lecture, which starts with an apology for my voice, which is not in the best shape, but I have this nice microphone. If you can't hear me, complain, but I'll speak very softly. Okay, so this lecture is kind of the math camp of the summer school. Some of you know a lot of math, and so I'm going to try to throw in as much that I can that's interesting for people who know a lot about networks, but at the same time, I'll try to cover enough of the basics that some of the recurring, words that'll come up will make more sense to those who are just starting to learn about networks. Obviously, an hour and a half lecture is not going to be enough to really cover all the tools. If that were the case, then I would quickly be out of a job. So I guess let me tell you what the plan is, and then comment on sort of the level of depth that I'm thinking about. So we're going to go over basic notions, emphasizing the ones that Matt didn't spend so much time on in his lecture. We're going to do a few applications which are really intended to be just practice using the words, although they might be interesting in their own right. We'll mention a little more we'll sort of continue naturally with the topic that Matt started with, sampling biases, and how that introduces, depending on what you care about, that determines how you want to think about sampling a network and how the structure of a network influences the statistics that you'll get when you sample. Meaning, draw someone, look at some attribute of theirs, and how is that going to, depending on how you draw them, how is that going to bias the estimates? And then really what I think of as the main course, and the thing that this is all going to be building toward, is starting to discuss network centrality and some notions that are quite central. They keep coming up, and they relate to the Arrow lecture that Matt's going to give into a lot of the different topics. It's probably the closest to a unifying mathematical theme that this literature has beyond the idea of a graph itself. And so I want to start with some of the fundamental mathematics of that. Now, overall, especially in that part, I'm not going to, an hour and a half is not enough to give full derivations. Don't plan to follow every step. For some of you, this will be a reminder of stuff you already knew, and then this will serve to emphasize what we think is important. For some, it'll be a challenge. It'll be stuff that you find easy to figure out once I alert you to its existence. And for some, it'll be a confusing first kind of flag in the air saying, this is an important idea, read about it on Wikipedia. So, So I also want to say, following up on a question that was asked in the first lecture, that think of this as a sign, like a warning, entering low motivation zone, not the way that inner city school is, but the way that pure mathematics is. I'm not going to talk about why. I'm going to say we want to study this thing about a network. I'm not going to tell you why. You can ask, but even then I won't tell you. Because that's what the rest of the lectures are about. So I'll take it for granted that the things that I want to study will matter for something, and we're going to focus on the mathematics we use to study them. Okay, so reminder of what Matt said. We usually don't write the n part of the network. When we don't write what set we're talking about, we take for granted that it's the numbers 1 through n. And people make a big fuss over whether a network is like a set of edges with weights on them, or whether it's, for me, it's just going to be a matrix, just this tuple of numbers indexed by I and j. By default, I'm going to think about graphs here in this lecture as directed and even weighted, but I'll tell you when I'm turning that off. So just reminder, undirected if the adjacency matrix is symmetric, unweighted if all the entries of the adjacency matrix are 0 or 1. There's an edge, also called a link or a tie, especially in sociology, between I if the weight is not 0. Okay? At this point, people often ask, is epsilon really so different from 0? It turns out for some asymptotic properties of what you do with matrices, it matters a lot. So there is some excuse for keeping track of whether something is or isn't an exact 0, in addition to the fact that that's often how we measure things. And what else is there to say? Often our graphs will be non-negative. So almost everything I say today, these matrices are non-negative. So here's a picture. I'm going to follow the same convention that Matt already introduced, that if something is in row number 1 and column number 2, like this 1 here, that means it's an arrow from 1 to 2, labeled by the number 1. Okay, so now starting with some words Matt didn't mention. So a walk of length L is a sequence, confusingly, of L plus 1 nodes. That's because they're L edges. So some people define a walk as a sequence of edges. Okay? But in any case, there's a L, it's a walk that takes L steps. For example, a walk here is this guy, and then maybe we can take a self step like this, right? So going from 1 to 3, back to 1, and then to 1 again. That's defined as a walk. And the path is a walk that repeats no nodes. Exercise number 1. So I'll point out, by the way, this is posted, let me go back. Here's a good excuse to take out your computer and do something better. Since I didn't have time to print, you can follow the slides here. And as we go, I'm going to mention exercises that come up, and I encourage you to go through later, and all the statements that I sort of went quickly through, you can work out for yourself. Okay, so a path is a walk that repeats no nodes. Exercise, in every walk, inside there's a path. And the shortest walk between 2 nodes is always a path. Because if you have repetitions, you could just cut them out. A cycle is a walk that comes back to where it started. For me, so walks are definitely allowed to repeat things, and cycles are also allowed to repeat things, nodes or edges. The standard terminology for a cycle, so for cycle it varies, but in this religion, a simple cycle is one that does not repeat. Okay, so cycle can repeat, except at the end. Yeah. So yeah, no repetition of edges. Okay. So here I've just put up a copy of the same definitions I just went through. Important definition, connectedness, okay? So here we're talking about weighted, directed, whatever. Now that we've defined what a walk is, I can tell you that a set is connected. It's a subset of nodes. I'll say a subset of nodes is strongly connected if for every 2 indices, every 2 nodes in that subset, you can find a walk from one to the other. Note the subtlety that directedness introduces. It may be that there's a walk from me to you, but not from you to me, right? For example, a directed line. So strongly connected means that you can go both ways. A strongly connected component, which Matt already informally referred to, is a strongly connected set that I should say non-singleton. It's a non-singleton strongly connected set that you can't make any bigger, keeping it strongly connected. So here's an example. This is a graph. It's a directed graph. And I've highlighted the strongly connected components. So you can see that some guys, by this definition, these guys outside are just singleton strongly connected components. You can't, if you can't make them any bigger and have a strongly connected graph. So this is the typical situation. A typical directed graph can be split up into strongly connected pieces that don't have any edges between them. If they did, one of them wouldn't be strongly connected. And then some guys outside who have paths to the strongly connected components, but nowhere else. So here's a simple exercise.
You can have one edge from component 1 to component 2.
No, I mean if there was an edge. Oh, I see what you're saying. Well,
Yeah, but not back.
no, but then we wouldn't say. I think you would. This wouldn't be.
What's your definition?
No, then in my. No, it's a maximal. If you.
Maximally strongly connected set. So take M prime, forget the other two there, and make just one edge from one node in M to one node in M prime. That's it.
Okay.
Then you still have those two connected components, strongly connected components.
Excellent challenge for the group is come up with a correct definition of a strongly connected component. How should we define it? So forget about this for a second. So definitely a strongly connected component has to be strongly connected. And I want to rule out this situation, right? Could I what? Well, so I want to capture, look, so I want to capture the notion of carving up, if you know Markov chain theory, I want a definition of the closed communicating classes. So I'll tell you a definition in words, right? We'll say a component is closed if there's no edge exiting it, okay? So these guys are closed because there's edges inside, this set of nodes is closed. There's no edge going from S to S complement, okay? So I guess what I mean by strongly connected component, Matt, help. Is it maximal closed? Maximal closed, okay? So this will be corrected, and strongly connected component is maximal closed. Exercise, in any strongly connected component, there's a cycle that contains all nodes. You can, remember my cycle is allowed to repeat nodes, so you can take a long walk, visit everyone in a strongly connected component. You'll find that errors have been strategically scattered for pedagogical benefit. Okay, so here's a notion that I'm not sure we've seen yet, although of course it's a natural one. So the distance from I to j is the length of the shortest walk from I to j, which happens to be a path. So this is a metric, by the way. If you like metrics, you can make your exercise that's not written on the slide, make your graph into a discrete metric space where this notion of distance is a metric, right?
Except it's not symmetric.
Okay. So in a undirected graph. So good. So it's, as Matt pointed out, it's valuable to keep both directed and undirected in mind. So for undirected, it is a metric, right? Because it's symmetric, but directed, it might not be symmetric. You might not even be able to get back to me at all, let alone in the same number of steps.
So that could be.
It could be infinite, right? So we'll define, so and relatedly, exactly. So the
Can't you have a definition of the length from one node to the other? I mean, you have another term. GI.
yeah. So it's the distance from I. This is a weird distance because it's from I to j. So it's
GI. I said, there's a G.
No, you only count GIJ as positive.
You only kind of, so far you've only used, but the option would be to put GIJ, G sub IJ. So the length could be the sum of the GIJs as you go along the path.
or the product, yeah, or depending on which. But
Maybe I haven't thought about that.
yeah, but yeah, good. So there are ways of, this is a very discrete notion. So here,
If you want to put it like a cost.
exactly. So right, so when people study shortest path problems in CS, they would think of this as like if the edge is how long it takes you to traverse it, in like a traveling salesman problem where you want to figure out how to efficiently visit places, then edges would have costs, and then we would define the distance. I mean, here we would define the distance as Professor Arrow suggested as the sum of the labels or the weights. Here I'm thinking of a very discrete notion of distance, which is just the length, the number of steps, and the two are equivalent in an unweighted graph where. No, well, this is my definition for the moment. But I don't want to. In order not to argue, let me just say that this definition is restricted to unweighted graphs, and then and the diameter of such a graph of an unweighted graph is the maximum of Dij across all I and j. It could easily be infinite, right? So if you just have, say, two nodes that don't have an edge, the diameter of that graph is infinite. So often we think about diameters of components to make it interesting. We think, okay, we're going to decide who's connected to whom and who's not, and then we're going to study the diameter of various components. But this does introduce troubles with statistics, because if you want to compute network statistics, these are very fragile properties, right? It's easy to mess up the diameter just by adding one isolated node. So you have to make decisions about how you manage those things. Okay, so, and one more, the average path length, which is a little confusingly named because it should be average shortest path length, is the average of the distances across all distinct pairs ij. So you weight them. There's nothing, this also makes some arbitrary decisions, like every pair is weighted equally, but people study this thing. This is a somewhat less fragile notion than diameter, because it averages over everyone, right? So it doesn't matter if it's really hard to get from one place to another place very far apart, as long as most people are. So if you remember clustering from Matt's lecture, a slogan is that real-world social networks tend to have high clustering and low average path length. And in a famous paper, Watson-Strogatz gave a simple generative model to produce both those features, which, for example, Erdős-Renyi, which was already mentioned, doesn't exhibit. Okay. So the out degree of a node is defined to be the sum of all, now we're actually going to sum weights, so it's the sum of all the edges, the sum of all the weights, the g's, that exit I, so from I to j. So we sum up all those exiting weights. That's the out degree. The in degree is you sum up all the entering weights. As Matt mentioned, disagreement, it all looks good here because our graphs don't mean anything yet, but when they start meaning things, these aren't always the intuitive notions of in and out, and so prepare for those headaches. As Matt mentioned, let me just introduce a notation. The degree distribution of a graph is just defined to be the empirical distribution of degrees. So it's mu of d is defined to be proportional to the number of nodes with degree d. Here again, this makes a lot of sense if you think about the discrete case, the 0, 1 case. And if we just divide. So here's an example. This is actually from Feld's friendship paradox paper. He has a distribution of, this is a survey of girls in a school. It's called the Marketville School data. And this is the graph. And this is the degree distribution. You've already seen sub, so we just count up, for example, how many girls have 2 friends in this data. Okay, so let's finally see something, let's see our first, some kind of fact or some kind of
Mini-lemma.
Yeah, mini-lemma. So let's take an unweighted, undirected network with no loops. This will be called, I will abbreviate this mouthful by simple network. In this case, di, of course, is simply the number of your neighbors. It doesn't in and out are the same, okay? And suppose all degrees are at most d. There's an upper bound. Big D is the maximal degree. So here's a little exercise that we'll do together. Let's try to find a lower bound on the graph's diameter and average path length in terms of the number of people in the network and this maximum degree. Okay, and then we're going to see another exercise which is a little more interesting. We're going to fix a maximum degree and think about our graph becoming very large. Okay, this is just to try to convince you that even in this bookkeeping section of the talk, there's a little bit of math or a little bit of things that might not have been obvious to you immediately. So if you have a connected graph that's big enough, then for most pairs of nodes, let's make most rigorous as more than half, okay? So for at least half the pairs of nodes, although you can make stronger statements, the diameter will be only a little bit less, only a small percentage discount on the diameter of the graph, okay? So most nodes in a graph are really far apart from each other. And let me show you how, this statement may be false too, but we'll see. But I'll show you the reasoning behind such arguments. So the key idea is if you have a graph, remember it's undirected now, so everybody has degree at most d. The number of guys you can reach in L steps is at most d to the L, right? Even if you were branching the biggest amount you could at every step, you couldn't reach more than d to the L that are distance exactly L from you, right? So if I want to count up how many I can reach in L or fewer capital L or fewer, I should just add up all these. This is a somewhat crude bound, although, well, not that crude because it's exact in trees. But if I add up,
Delta and D are the same.
no, yes, sorry, this should be capital delta is the same as capital D. So this is an upper bound on who I can reach in capital L steps, okay? I even have an explicit expression for it if you want. So now I'm not going to write out, we're not going to do the arithmetic of, or the final steps of algebra to use this. That would be more rewarding to do by yourself. But you can see that this expression will give us two kinds of facts. One is it'll give us a lower bound on the diameter of the graph, because it must be that we can reach everyone in the diameter number of steps, right? So if we put diameter in here, this should be at least as big as the population size, and that'll give you a lower bound on L. So that already means that as a graph becomes very large and the degree is bounded, it must be that the diameter is growing, okay? And also, it'll give you an upper bound on what you could reach if you only decided to take some fraction of the, so if you decided to say, well, I'll go only 75% of the diameter of steps, how many nodes would I reach? So using this formula and using your knowledge of logarithms, you can convince yourself that you won't hit most in 75% diameter number of steps. So this is a good exercise to play around with but you could, to me it wasn't obvious that most nodes in a graph are as far apart basically as it's possible to be. And also I have a story, which is that when Matt and I were writing our naive learning paper a long time ago, I wrote him an email and I said, Matt, I'm so excited. We were trying to characterize sufficient conditions for something, doesn't matter. I'm so excited. I found a sufficient condition which generates this amazing theorem, bounded degree and bounded diameter for arbitrarily large graphs. Okay, so as long as you assume that Matt, very nice. This as
You can also prove that 1 plus 1 is 3.
exactly. Matt said that in a more polite way. So not knowing this fact is a good way to prove vacuous theorems. Okay, so let's do a little more. This is going to touch on what Matt said. So remember, out degree, in degree, degree distribution. We saw this slide. Let's come back to it now. So you saw the friendship paradox. I've put it up again. Let me say a few things here. So there are a lot of, if you go read a graph theory book, there are a lot of theorems about graphs. Some of them, are a little bit like this, like the sum of in degrees is equal to the sum of out degrees. Okay, you can convince yourself of that. Here's here's a definition. A bipartite graph is a graph where you can divide it into two pieces, like the boys and the boys have no edges between them, and the girls have no edges between them. All edges are across. Okay, so if let's say you have a bipartite undirected graph, it must be that the sum of degrees on the left is equal to the sum of degrees on the right. So for example, if you ask people about their number of sexual encounters over the past year, in an appropriately defined population and so forth, there's accounting identities that will sort of enforce honesty. You can check whether, and in fact there is misreporting according to that standard. So some of these accounting...
There is a famous book in sociology written stating the following empirical fact. The average number of sexual partners of men is 2 and of women is 6.
Yeah.
With no comment whatsoever.
But I never know. I mean, if they meant median, then there's no problem, right? So it's
No, said average.
okay. Well, but in middle school
I'll find you the reference.
But is average always the mean? In middle school, I learned that average could be the median too.
They meant average.
What do you think?
No, it's been used to discuss the accuracy of the data, obviously.
Yeah.
Of course. With the,
At least some comment is needed
No,
once
yeah,
you make the
it's
statement. Because and now the conventional story is that Aumann went to talk to the guy that wrote the book, and who was in Stony Brook, I think, and the guy didn't understand at the beginning that there is an issue here to explain. That's sociology.
Actually, I have something to say about. I have something to say about that too. So let me remind you. So So right, so those kinds of accounting identities, they don't, Sergio thinks they don't even, they are too obvious to say. You can convince yourself of this kind of stuff, okay? But I would say the friendship paradox is a little bit non-obvious, right? You thought that that you needed to assume something about the random graph. And let me just remind you of the statement that Matt said. So you have an undirected graph without loops and with no isolated nodes. So Matt just did it with one component. Turns out this is the same. If you define delta I to be for Mr. I looks around himself and says, what is the average degree of my neighbor? That's delta I. Then, as Matt said, the average of those, so the average, everybody does this local evaluation. Then we take an opinion poll and we average together everyone's impressions. And that average exceeds the true average degree. Okay? That's the friendship paradox. And Matt gave conditions for the inequality to be strict, and he gave a proof. Now, Scott Feld, actually, when he wrote the paper, this is not the version of the friendship paradox he stated. Matt cleaned it up for you. And I'll show you something. So this is a good, Matt's proof went quickly. It's fun, to try to puzzle this out yourself. I would say it's kind of a medium problem set question. So it's worth kind of seeing how you would have proved it. But let me give you another view. So forget about this for just a second, and let me give you a related phenomenon, but I'm going to present it sort of from scratch. So again, take a simple network. Remember the definition of the degree distribution. Now, suppose that we were to take a node uniformly at random and say, what's your degree, Mr. I? What's the mean of the random variable? So this gives us a random variable. Whatever he says, that's our random variable. The mean of this random variable is, of course, just the mean of the degree distribution, right? This is the probability that we select a guy who happens to have degree D, and then when we select him, D is what he says. So if you sample uniformly at random, ask Mr. I's degree, you're going to get the average degree. Now suppose you do something that sounds very similar. You draw an edge uniformly at random, and then you choose one of its nodes uniformly at random. Okay, so maybe you think, when would you ever draw an edge uniformly at random? Well, here's a way. You pick a person uniformly at random, and then you have them pick a uniform at random friend. Now you've selected a random edge, okay? And ask the guy on the other side of that edge, what is his degree, okay? So that's the degree of a randomly selected friend. It's a random person's random friend. And you can ask, and then you ask that guy his degree, okay? So what do you get? Well, as a piece of notation, let me just define mu tilde to be the probability of sampling a guy with degree D in that two-step exercise, okay? And now we want to know, this of course will be the mean of the answer, but that doesn't tell us much without knowing what this mu tilde is, right?
But you said draw an edge uniformly random.
Yeah.
So you want to draw uniformly now?
No.
Because that's not called dropping. Drawing an edge uniformly means look at all edges, choose one of them, or each one with the same probability.
Yeah, my claim is...
It's not the same as choosing one node and then choose an edge from that node. It's not equivalent.
Those are...
No, they are not. Because
You're
a
right.
node that has many edges, then you that's no longer uniform over edges.
Oh, I would have to draw, right. So I have to draw a proportion to your degree. Okay, so forget, yeah, so let's say...
Which model do we take?
Take this model, okay? So I'm going to take the draw edge uniformly at random. But before we go on, let's figure out what realistic procedure could we think of a way to sample an edge uniformly at random. So if you want an interpretation is easy to give. Suppose these people are talking, okay? So every period, everybody makes a phone call to all their friends and says, I think that stocks are going up today, okay? So every pair of friends has a phone call. Suppose I listen into a random phone call, okay? Now I've selected a random edge. So that's a story. But Sergio is quite right that my other model, random person's random friend, is a different distribution. Okay. So let's study the first model, and maybe we'll come back to the second later if we have time. So tilde mu d is the probability of drawing a node of degree d in this procedure. And it turns out that what this tilde mu is a perturbed version of the original degree distribution, where the tilde probability of drawing degree d is the original probability of drawing a guy with degree d times d, okay? It's proportional to that. You have to normalize to make it a probability distribution. That's because when you draw a random edge, a guy that has twice the edges has twice the probability of being picked, okay? So there's, let's suppose there are only half as many guys with degree 10 as with degree 5, okay? But if I draw a random edge, I'm going to actually pick them, I'm going to find them with equal probability. These degree 10 guys and degree 5 guys are going to be found with equal probability on the ends because the degree 10 guys are advantaged by their extra edges. Okay? So a node's probability of being chosen is proportional to the number of edges it touches. Okay? So the implications of this are, Matt I think went through the sampling implications. When it comes to, if, for example, looking, the typical relationship is not representative of the typical person, right? Because some people have more relationships, and the friendship.
The second moment.
Good. So if we want to now know what the mean degree of a random friend is, of a random end of an edge is, then it's going to be, right, so in here I have 1d coming from this part, right? That's what the guy will say. And then the probability of selecting that guy is d times mu d. So I have a d squared, okay? And the bottom is just a normalization. Remember I told you I have to add up, I have to make the probability sum to 1. So I'll add up all these d times mu d, all these, I know that the probabilities are proportional to this, so I'll sum up all the numbers to get a normalized probability distribution. So this is the answer as contrasted with, just the regular old mean. And of course, that's just the second moment of the degree distribution divided by the first moment. Yeah. So a theorem is that's bigger than the first moment. Now, Matt, do you remember, was Feld talking about a random, I think he was talking about this, right? This is the...
Yeah, so Feld's discussion is a little bit confused. So the sampling wasn't spelled out correctly. So you can make it reverse sampling, but you have to do the process.
Yeah. So he talks about, so if you want, Matt mentioned that sometimes we just care about the pure structure of social networks for its own sake, and I think that our the social networks tribe in economics has taken over this quantitative sociology more or less, and if you want to see why that's a good thing, you should go read Feld's original paper from 1991 called The Friendship Paradox, because it's not very clear what he's trying to say, but these are the quantities he studies, and then he observes that this is bigger than the first moment, and that's his proof of the friendship paradox. But it's not clear what, as you could see in my discussion of this, it's not terribly clear what these quantities are supposed to mean. And so I think Matt's quantity is the right quantity. Now, relatives of this thing, so it was, so on the other hand, this formula is a nice formula. And as you'll see when we get into the lectures on diffusion and related things, sometimes these kinds of draw, the other exercise draw.
That's the one that, if you want, what Matt gave is not this one.
No, it's not this one.
You have to give equal weight to the nodes because you are averaging over nodes. So the model that you mentioned is the right model in which you want to check the formula, not this one. You don't choose an edge at random.
Right.
You choose a node at random, and then you choose one of its at random, equally likely one of its neighbors.
Right.
That is what you want to do. This is a different model, and that.
Yeah, although as you and I discussed recently, it depends. Sometimes you do want to weight guys by their degree, right? If you, for various, statistics, you might want to actually sample in a degree biased way. But this quantity. So keep this guy in mind, because when Matt and Liat lecture on diffusion, you'll see that a lot of the analysis of those models comes down to reducing things to various moments of the degree distribution. And this is a first taste how, in a very simple and unmotivated sampling procedure, you see a higher moment of the degree distribution come out, right? I guess just for completeness, I should say, I'm going to use the small sliver of the board aloud. Remember that the expectation of the square is the square of the expectation plus the variance. So that's why that's bigger than the mean of the degree, and those things will come up again and again when we study diffusion on networks, but I will let the people who are lecturing on that do that. Okay, so this illustrates one other thing. So what Matt did for the friendship paradox, for sort of the correct version of the friendship paradox, was an exact computation that verified kind of the correct inequality in any graph. This is a sort of more casual exercise, but the answer is easier to parse than the answer he got, which involved all these di over dj kind of things. This is still a little bit messy because the expectations here are over the empirical distribution, right? You have your real graph, and this is just the empirical, the average of the d squared over the graph that you actually have. Oftentimes, people take generative models where they say, let the degree distribution be Pareto. Okay, well, there is no graph like that. Certainly no finite graph, because it only has finitely many nodes. It can't have infinite degrees. But oftentimes what you'll see is people work with these kinds of quantities, and they just casually replace what should really be empirical averages with just the average drawn from the distribution, the degree distribution that the graph has an expectation.
That works, that's all right for large.
Sorry?
For large sample, that's all right.
That's right. So there are laws of large numbers that formally justify that, but there are a lot of subtleties. So just as a methodological or philosophical matter, keep in mind when you're doing a mean field analysis, there's some step where this would be replaced by the expectation of the ex-ante distribution, and you should worry in the back of your head, is there a law of large numbers justifying that? And of course, there's an industry to making things rigorous, and I think sometimes we worry a little too much about rigor. For my taste, you learn a lot by being casual, but you should always put a little star where you've, replaced sample average by a ex-ante average. So that was that reflection. So far, a matrix for us has just been treated as a box of numbers, okay? Everything we have done has been bookkeeping. Like, the bookkeeping kind of networks math is that the average number of sexual relationships per man is the same as per woman, okay? It's not a profound theorem. We can certainly already see some things that, as Matt highlighted, that this should make us careful about how we measure things. There are certain biases in selection or observation or whatever. But, you might ask, is there any, if we're representing these things as matrices, can we actually get anything out of the linear algebra of that representation? Can we do more than treat the matrix as a box of numbers, get something out of thinking about it as a linear operator? I heard a statement I once heard attributed to you is that all math is in some sense bookkeeping math, right? From the perspective of a very smart alien, all math is just people saying to each other, I think 1 + 1 = 2. All math is a tautology, but some tautologies are less obvious than others. So I'm going to try to show you that some of the less bookkeeping things we can do with matrices. So let me do. Remember, I warned you about unmotivated. So here's an unmotivated exercise. Let's take a connected simple graph. And let's define, so this is just a definition. There's a typo here actually. This should be set, okay? I'm going to think about the set of walks, and then I'm going to think about the number of walks. But let this calligraphic thing be the set of walks from I to j that have length exactly L. Okay? So that's just a definition. And say we want to understand the size of this thing. We want to count with repetition.
With repetition, okay.
And we want to count the walks. Okay? So I want to count how many walks are there of length 10 from me to Jan in this graph. So let me give you at least a loose motivation to make this somewhat easier to think about. Suppose that there's some rumor going around, and a person who sort of has the rumor, actually think of it as a potato, okay? So a person who has the potato picks a friend uniformly at random, and gives a potato to each friend. So the potato's clone, okay? And you have all these. So every time you have a potato, you make as many copies as you have friends and keep passing them around, okay? Think of these as messages or statements or rumors. And we want to count, how many potatoes will be in transit after some amount of steps. If there's some probability that they disappear, they get stolen by some kind of force, will we expect the process to go on forever, or will at some point it die out? So it turns out that this frivolous motivation actually is not the one you care about, of course, but these exercises, counting walks, are going to come up a lot in game theory, in communication on networks, and in financial networks, in a variety of applications. So just trust me, you're going to want to count walks, so let's learn how. So here's a fact. The number of walks of length L from I to J is exactly equal to the following thing. You take the adjacency matrix of this graph, you raise it to the nth power, and you look at the ijth entry. That's the count you want. Okay? Some of you have met this fact. Learning this was a revolutionary moment for me because it made matrix multiplication make sense. I don't know what what g to the 7th really is, but when you think about it like this, it gives it sort of a simple meaning. And it's easy to see why this is true. You could just prove it inductively, okay? The way you make walks of length L is you take walks of length L minus 1 and you add on an edge. So the way you get a walk from someone far away to me of length 10 is there's a walk of length 9 maybe to Eric, and then you just throw in the Eric to me edge. So if he has 32 walks from you to him, then that gives me, of length 9, that gives me just from him 32 walks of length 10 by just adding an edge, right? I add that edge and then I extend each of those walks into a separate walk to me, okay? And it turns out that's exactly what matrix multiplication computes, right? So if you believe me, the GL to the minus 1, its ijth entry counts the number of walks from I to j of length L minus 1, then when you multiply this by another g, right, let's look at Mr. 1 here. Here you see, so let's suppose we're curious about the number of walks from Mr. 2 to Mr. 1 of length L, then the matrix multiplication tells us we should look at this, right, second row, first column. And each of these contributions will be exactly the story I told about Eric, just extending those walks by an edge, assuming there's an edge. Question?
So, but it's not just, I think it has to both be backwards and forward equations, right?
What do you mean by backwards and forwards?
This is just like Markov chains for the symbol, right? For the transition matrix.
Yeah.
And it has both the backwards and the forward property.
Well, so these are, if I'm counting, I think I'm okay if I'm counting directed walks. So this statement is more general than the Markov chain facts, right? If I just want to count the number of directed walks from you to me, I count all the directed walks to someone else and then extend them if they have an edge to me, directed edge to me. So as long as you keep track of directions, this statement is absolutely general. I'm considering unweighted, okay? So actually, right, so simple for me has meant undirected, but directed is fine for this part. But let's keep the 0, 1 thing to avoid getting into how to weight the walks. Okay, so you can convince yourself that matrix multiplication has this walk counting interpretation. And a question you might want to ask is, how quickly does the number of walks of length L between I and j grow as you consider longer and longer walks? Remember, since walks allow repetition, for example, if you and I have edges going both ways, from me to you and back, that adds a walk every time. Every time you allow me 2 more steps, I get another walk by just walking in this circle, and I can walk in other circles too. So the growth is interesting, again, for purposes like asking basically whether a certain propagation will die out. Matt was talking about feedback earlier, right? In a lot of network processes, we have people influencing each other, and then that echoes back to me because I'm influenced by them. If you want to know whether these echoes kind of die out or whether they can grow, you'll basically care about counting, it'll turn out that these kinds of quantities, these kinds of matrix powers, capture the L-step indirect effects. And so if there's some dampening on them, you want to know, is that going to be enough to kill them, or will the feedback loops, the many different avenues of feedback, blow up so fast that they'll overcome the damping? So it's this kind of horse race that we want to study, and I'll give you formulas that refer to that. But let's just suppose you were a mathematician and cared about looking at the growth rate of these walk counts. So there's a very nice, simple set of mathematical facts which will answer the question for you. Take your graph. So now we're going to make it undirected, okay? For the rest of, I'm going to say a bunch of, there are generalizations, but let's do the easy undirected version. So G is a symmetric matrix. Because G is a symmetric matrix, we can diagonalize it. We can write it as S times lambda times S inverse, where lambda, this matrix, is a diagonal matrix with some numbers on the diagonal called the eigenvalues of G. Okay?
Or simple, goes both ways.
So this is an undirected. Yeah. Now I've specialized to undirected. So if you stare at this for a second, right? Let's remember what's the point of expressing things this way? It's mainly so you can do this. Okay? So you can understand the powers. So even just 5 minutes ago, trying to think about the powers of G, you got a little bit of a headache, right? But once we've diagonalized, the beauty is, for example, that G squared is S lambda S inverse S lambda S inverse, right? So these middle parts all collapse, and you just get S lambda squared S inverse. And obviously that will work as many times as you would like. So understanding how this matrix behaves under taking powers boils down to understanding how this diagonal matrix behaves under taking powers. And indeed, so we'll see in a moment. I'll give you a fact, but this matrix will always have it has all real eigenvalues. That's another consequence of being symmetric, and it has a positive one. So I want to focus on the biggest positive eigenvalue. Once you've written things like this, you can see that the behavior of the system, if you raise it to high powers, right? Suppose there's an eigenvalue of 7 and some eigenvalues that are smaller in magnitude. It turns out that there's always a positive eigenvalue that's the biggest one. Then that thing will basically dominate the behavior of the system, right? If you want to compare relative entries, the biggest entries in this matrix by far, when you take L to be big, will be coming from the dominant eigenvalue, this biggest one. So in fact, this is not supposed to be completely obvious, but it can be shown, and we'll actually see a little bit later, that the number of walks between you and me for any I and j is basically, to first order, just lambda 1 to the L. So lambda 1, the largest eigenvalue, the magnitude of the largest eigenvalue, describes how fast these walks kind of pile up. So as you take, it's an exponential growth with base lambda 1. That's a fact. So this walk counting exercise, at least asymptotically, can be reduced by this linear algebra to this formula. And the slogan here is that, so what is the point of eigenvalues? I love eigenvalues very much. The nice thing about them is that it makes a matrix more like a number, right? I'm not so good at thinking about what matrix powers mean, but I'm good at thinking about what number powers mean. And eigenvalues allow us to, in a precise sense, reduce the study of matrix powers to the study of powers of numbers. Question? That's right. So we'll see in a moment that the columns of S are actually the eigenvectors. Yes, soon. That's coming. Okay. So this was meant to be a little puzzle or a little exercise to get us to meet these objects. If you want to do stuff related to like the the lectures on public goods in networks, games on networks, the stuff I'm going to talk about on Friday with learning or information diffusion in networks. Knowing more about these guys will be helpful. So my favorite reference is a book by Karl Mayr called Matrix Analysis, but obviously any respectable linear algebra book will.
Is that problem double of movements?
Yeah, so good.
The power get another, it's exponential over the linear.
So in this case, in the symmetric case, so if you have a connected graph, then there will be exactly one. So you could have, the worst thing that could happen to you is that you have -1 as an eigenvalue. So you have an eigenvalue that's exactly the same magnitude as the biggest, but on the minus side. So if you have a bipartite graph, you would have.
Otherwise you can't get it. You get a double.
You can't get, no, with this, we'll see later.
Symmetric matrix, the roots are real, but doesn't mean they can't be, you can't have one.
Right, so for the dominant eigenvalue, for the biggest one, its multiplicity counts the number of components in the graph. So the Perron-Frobenius theorem says as long as your graph is strongly connected, you're not going to have multiplicity. Okay, so if you want to know more, Mayr has a really beautiful, it's like a picture book. You can sort of browse through it and learn what the stuff that because this was always very intimidating to me until some point, and then he really just explains why all these facts are true. So I highly recommend him if you would like to demystify it. So let's discuss now, going to the question. So I should amplify the question in the back. It was: is there any meaning in this diagonalization process? I focused on the eigenvalues, which captures the growth rate of the walks, how fast the number of walks amps up. But is there any meaning to this other bit, this S that we use to diagonalize it? The answer is yes, and that takes us into the study of centrality measures. So in a sense, some of these eigenvectors are going to capture. They're actually going to capture a lot of the structure of matrices and that of social networks, and that's one of the most fun themes that's going to run through a bunch of the lectures. But let's see some of the first things that you can fish out of these decompositions. So let's forget about walk counting for a second and talk about the more fundamental question of how might we try to understand who is central in a network, who's important. So Matt already mentioned the most basic notion of centrality, which is, do you have high degree? If you have a lot of connections, you're central in one sense. You could also think of yourself, but you might not want to think about just direct connections, right? Somehow the whole point of studying networks is we think there's more to it than just the direct connections. So maybe we'll consider you important if you lie on a lot of walks. Matt mentioned another notion, which is you lie on a lot of shortest paths. Then that kind of centrality is called betweenness. Or maybe you're important if you have short paths to a lot of nodes. That kind of centrality is called closeness. Okay, so you can look up the definitions of all of those in Matt's book, and I'm not going to have time to focus on most of them. But it's going to turn out that one of these methods of calculating centrality is going to relate to walks, and that's the one I want to. It's sort of in some ways the nicest one mathematically, and so that's the one we'll talk about now. But I want to point out that these notions, there is no. I think part of the point of doing economics with networks is we put some meaning on these. So sociologists are happy just to have a zoo of measures. You have betweenness, centrality, and you kind of are an artist intuitively picking the one that seems interesting to you right then. In economics, a lot of our work tries to provide micro foundations. When do you care about? When is this kind of centrality the kind that matters for some economic outcome? And so that's kind of a unifying theme. It's not reverse engineering exactly, because oftentimes we don't bump into any of the familiar ones. But for some nice economic applications, it turns out that what matters is exactly a centrality measure that sociologists have been studying for a long time. So we'll do something unusual in an economics talk. We'll actually meet the centrality measure as an abstract object before we meet it as the answer to some economic model. So let me introduce you to this Katz-Bonacich or Bonacich notion of centrality. So let me introduce it by relating it to degree centrality. Okay, degree centrality is a very simple idea. It's the number of links you have, or the sum of your link weights if they're weighted. The basic idea of Katz-Bonacich is that it is not going to count all links, even in a graph where the links don't come weighted by themselves. It's not going to give equal weight to every link. It's going to weight them by how important is the guy who is at the other end of that link. And it's also going to allow a valuable generalization, which is, it's going to allow you to say sort of, you have some pre-existing notion of importance. So without further ado, let me just put a formula up. The basic formula is people say your centrality is going to be proportional to, this lambda is capturing this proportionality. Your centrality is proportional to this counts your friends, right? Let's say G is 0, 1 again. So this is just one entry for each friend. But not all friends are equal. Friends who are more central are going to contribute more to your centrality. Okay, that's the first term. And then I'm going to allow some BI, some base level of centrality that you get kind of not from your friends, but from yourself. Okay? So one way this was introduced, this idea actually has a long history, and it existed, I think, even to some extent before these guys. There are papers from the 50s that you can find in bibliometry. People were trying to find basically good citation measures. And so, there are many interpretations, right? You're an important scholar if your work, let's have the graph of citations. If you're cited by other important scholars, so Gij is I is cited by J, proportional to how important they are, but maybe we'll allow we have some other measure of how important you are that has nothing to do with that, and we'll allow that to be thrown in too, okay? So that's the basic idea. If we write it in vector notation, what this says is that some constant lambda times the C vector, the centrality vector, is G, the matrix, times the centrality vector again, plus this vector of base centralities. Okay, so this is the basic. These guys, so what happened historically is people said, hey, this sounds like a good measure, let's use that. Okay, so let's understand some things about it, and then you'll see that it is related to equilibrium behavior in certain kinds of games. It's related to who's influential in diffusion processes, but let's just study this as an abstract notion. So let's do a little bit of arithmetic and divide through by lambda, okay? So I'm going to divide everything by lambda, and then I'm going to bring this G over to the left-hand side. And then I get that. Now, if I just define some symbols, okay, nothing is happening here. I'm just going to define alpha equals lambda inverse, and b tilde equals lambda inverse times the old b. I can write this system. I can save myself some letters, and rewrite the system as c equals. Here's the first rewriting. Right, just I minus alpha G times C equals B tilde. Okay, so that's just introducing some symbols. And then, once I've written it like that, the system is asking to be solved, so we solve it by making this equal to just doing the matrix inverse. Of course, assuming that this matrix inverse exists, right? So we'll come back to that. But assuming this matrix is invertible, then this is okay. Now, I don't have a ton of intuition for what this means. I don't know about you, but on its own, somebody shows me I minus alpha G inverse, I guess you can look up in a book the cofactor formula for the inverse of a matrix, but that doesn't mean anything either unless you have powerful determinant machine in your head. So I think actually one of the nicest things about networks, as a lot of people who are going to be talking here study them, is that they're all about giving formulas. Sometimes in macro, you'll see these systems solved. Like I was reading a trade paper, and they needed to, this came up actually. It was about tariffs, whatever. So they said, okay, this is the measure of market access. And they go on. It's just you solve it with linear algebra, that's it. But for me, this isn't enough. You want to understand what is this thing? What is the meaning of it? So it turns out, fortunately, it has a meaning. And so this is a formula that I really want to emphasize. The Neumann series, maybe I'll write, no, sorry, so this is not von Neumann, by the way, it's some other guy. But it's important enough that it's worth writing. It just says that you can think of this matrix inverse as a sum of these powers, okay? It's analogous to a formula you probably know, that 1 minus x inverse for a real number is this power series. So it turns out that a vast generalization of this, obviously this fact is a generalization of this fact, because you can make your G a scaling of the identity matrix. And this is going to give us a lot of insight into various network processes, because a lot of systems are going to be solved like this, and whenever you see this guy, or you can manipulate a system into looking like this, you'll be able to express it in terms of this and understand it in terms of walks. Okay, so I've now just copied, I've reproduced the most recent stuff, so it's still here. And so C, this C thing defined this way, is defined to be the Bonacich centrality with parameter alpha. This is alpha. And base centrality is B tilde. Now, I forgot to say something. This series expansion is not always valid, okay? It has some formal meaning, even when the assumption I'm about to say is not true. But when this formula is true in every way, you have to make some assumption about this thing. Basically, this stuff has to not blow up, right? Because if it blows up, then there's no hope for, this series won't converge. So the assumption is that alpha times G, this damping parameter times G, has to have largest eigenvalue at most 1. Okay, or to be completely precise, the modulus of the largest eigenvalue in modulus has to be at most 1. If that's true, then this series converges and everything's good. What does that assumption mean? So what does it mean to say that alpha times G doesn't have any eigenvalues that are bigger than 1? It means that G doesn't have any eigenvalues that are bigger than 1 over alpha, right? Because when you multiply a matrix by a number, you scale all the eigenvalues. So the assumption that's necessary to make this work is that the spectral radius, so if the spectral radius, which is the magnitude of the largest eigenvalue, is no bigger than 1 over alpha, then you're okay. Then everything makes sense and you can use this expansion. Yeah? Yeah, of course.
I would like to challenge the assumption that if you links have more links, you are more central. Maybe if you friends in Facebook and less friends, you influence more.
Yes, well, so that's not completely, if you allow this to be weighted, that's not ruled out by my, right? It could be that guys with, that if you believe that there are differences in how much influence I derive from my friends or whatever, then you can put that in the G's. So I may have fewer friends, but each of my links may be stronger to them. And that would be in the G's, and that would enter this formula that way. So this formula is making assumptions, and jokingly, if you're challenging that this makes, is good for measuring something, I have no problem with you because I haven't claimed it's really good for anything. We'll see what kinds of games this ends up being the solution to, and then you can judge those models. But for now, we just set this up. But you're right, other notions of centrality, like betweenness, will give completely different answers to this, right? You could have very low centrality in this sense, and your notion that having fewer links could actually be better in a way that's not even captured by this formula is also reasonable. So different centrality measures for different problems.
Right. This is so far from, as you have already said, from economics. Let's say we define centrality. There's something happening, some behavior.
Yeah.
To try and explain. what behavior lengths, but even remotely, let's say in a vaguest way.
Okay.
Centrality. What is it that we care about?
Well, so I mean, here's let me, speaking very loosely, here's something you could think. Let's think about industries in an economy. What makes you a big industry? If you trade with other important industries, right? If I do a lot of sales, I basically have to, the money has to come from somewhere. So if I have strong links to other industries that themselves do a lot of sales, that's going to contribute to this term. And maybe I sell to some foreign economy or something, so that's going to be the B. So it turns out that very loose statement has a formal analog that there's a sort of Leontief revival going on where people are taking the old Leontief models, where of course this Leontief inverse comes up, and getting them, solving macro models with endogenous prices and everything, where these kinds of equations pop out for the relative centrality of industries. This isn't saying anything very exotic. It's just saying you're important if you're in contact with important other nodes in some sense. And I think that's very economic, right? Because everything, it's an equation that says your endogenous position depends on the endogenous position of those near you. Yeah. Oh. Oh. This says in Russian, these are moist antibacterial napkins. And so I was wondering what sin I might have committed to be judged in need of them. But it's for the board. That's very kind. Thank you. No, I think the soft antibacterial napkins are what we have.
I'll try to get you.
I'm not going to be using the board that much.
You'll get something with bacteria.
Okay, so now, by the way, so this thing, I should say, Professor Arrow's comment reminds me that this thing is called the Leontief inverse by some people, because if you look at the old Leontief models, this thing also comes up. In that model, it was just looking at goods flowing around the network, and it's the same thing. You get a lot of goods flowing through you if you use as inputs industries that have a lot of goods flowing through them, right? So there's some kind of, these equations come up, they're just,
B would be, in the Leontief story, B is the list of final demands.
That's right.
Yeah.
And they somehow feed through the system and
And then C is the vector of primary factors.
that's right. So Leontief was in some sense the first centrality economist.
Well, it's centrality. You get the bigger the smaller don't have any...
Yeah. We call it, we stole it.
But the trouble is, the C, its importance of criticality is measured with, the C here is a demand by industry for primary factors.
That's right.
The criticality depends on whether those primary factors are there.
Yes.
The scarcity.
Right. So one thing,
So the important, there's a big demand for air in most production enterprises.
right,
Economic uses of no consequence.
right.
So it's not the size of C related to something.
Right. So when you have an application in mind, and we'll see. So for now, I'm just putting up facts about matrices, and we'll see that some of what Professor Arrow is pointing out, that how we should interpret what centrality means in a given context will vary a lot. And in fact, it depends a lot even on whether we choose to look at G or its transpose. So I encourage you to keep that in mind. But be that as it may, using the Neumann series, the Newman series, because it's not von Neumann, we can write this thing. So this just uses this expansion and writes the centrality as this sum of powers of G times stuff. And the interpretation, remember, we already saw that the ijth entry of G to the power L counts the number of walks from I to J of length L. Okay, that should say of length L. So what this is a weighted, what the Bonacich centrality with parameter alpha is basically let's take the simple case when this base vector is taken to be the same for everyone. Then it basically is your weighted walk count. How many walks do you have of length 2, 3, 4, down weighted by alpha to the length. Okay? So basically Bonacich proposed, without what we would call a microfoundation, that this is a good way to measure how important someone is. How many ways are there to get from them to other people? Okay? These motivations never sounded that great because, for one thing, it's not so obvious why we care about walks as opposed to paths, right? Why does this repetition add so much? So I want to raise this as a big question. We're after economic microfoundations, and we'll see a lot of them, but I think that it will be easier if you know all these formulas in advance, and then you can say, oh, okay, then once you get something in this form or in this form, you can use this.
One reason for walks rather than paths is that there's propagation which you don't control, and then it can't know if it has visited it already or not. So there is random propagation, then it clearly
Exactly.
walks rather than paths.
Yeah, so in a linear system with feedback, it's the walks that matter, as it turns out, because the propagation.
Yeah. You never know if you visited or not. I mean, the automatic system doesn't.
That's right. So,
memory.
exactly. That's right.
It just spreads out.
Yes. So you'll see another place where these kinds of weighted sums show up is in models often studied in macro, for example, where you study perturbations of systems, and then if I perturb here, that has all these ripple effects, and these walks add them up. Okay, so useful formulas for walks, and this is an important definition. So Katz-Bonacich centrality is, you can either define it as the solution to this equation, the C, or you can think of it explicitly as like this. Okay, let me tell you about another kind of centrality. It's very closely related. Remember, we had this equation. Now, suppose we considered a case where there's no base centrality. There's nothing coming from outside, okay? So everything is going to be defined just by the links. In some sense, this is the purest centrality question. I don't want to impose some external, input or whatever. I just want to say, I want to define the centrality of these people in terms of the links that exist among them. So that formula says that C is equal here when I've said b to 0, it says that the centrality of Mr. I is proportional to the centrality of, is just proportional to a sum of the centrality of those people, of his, let me say it like this. It's his links, the sum of his link weights, weighted by the centrality of those at the other end. So the cool kids are the people, the ones who are friends with the other cool kids, if ij is friendship. So if Gij means that I gets respect or attention from J. Now, you might look at this and you say, this is not tied down, right? There's nothing to determine, since this is all, this is obviously, C is on both the left and the right-hand side. How is this going to give you an answer? It turns out that things are better than you might have thought. So what we hope to do is to find a non-negative solution for C and non-zero. So this is really an excuse to introduce a theorem that it will really be helpful to know. So let me just slowly walk through the Perron-Frobenius theorem, which will give us this and many other nice things. So let M be an irreducible square matrix with no negative entries. Okay? Irreducible means that when you plot it as a graph, it's strongly connected. And let Rm be the magnitude or the modulus of its largest eigenvalue. Then we can make several statements that are certainly not true of a general matrix, which actually goes back to Professor Arrow's question earlier. So the real number, so this magnitude is a real number, right? It's an absolute value of something, so it's a number like 7. And it turns out that, but a priori nobody promised you that eigenvalue was not like -7 or an imaginary number, a complex number with magnitude 7. But it turns out that it's always true that there is an eigenvalue of your matrix that is positive and equal to that. There's a positive real number equal to the spectral radius. Another way of saying this is that the spectral radius is always achieved or realized by some positive eigenvalue. So the picture to draw, thank you. the picture I like to draw is if you have all your eigenvalues of your matrix in the complex plane, I'm going to draw a circle whose radius is just big enough to contain all of them, right? So this is the complex plane. I have eigenvalues here, here, here. And I draw a circle that's big enough to catch all of them. Its radius is the spectral radius. And the first part of Perron-Frobenius says there's an eigenvalue here. There's a positive real eigenvalue equal to the spectral radius. Okay? Moreover, it has a very special eigenvector associated to it. It's called P, it's called the Perron vector. It has only positive entries. We're getting this out of the fact that the matrix is irreducible. So it has an eigenvector with only positive entries, such that, and m times that vector is equal to lambda 1, this real positive eigenvalue, times p itself. So this Perron eigenvalue is associated with a strictly positive eigenvector. And finally, if you bring me any other non-zero vector with non-negative entries, such that this equation holds, so this is basically a pretender to the eigenvector thrown. This guy wants to satisfy this equation with some real number q, okay? Not necessarily, so it's just some eigenvector with a real eigenvalue. It turns out that it must be that it's actually the same thing as this p, and that the eigenvalue in question is equal to the biggest eigenvalue. So this is a long-winded way of saying that there is a unique non-negative eigenvector. All eigenvectors other than the special one will have some negative entries, okay? So those are all useful facts for various things that you'll want to do, and we'll even see some
This is that the dimension of the eigenspace of that is 1, right?
So because, irreducibility gives us that both the algebraic and geometric multiplicity of the Perron root is 1. I keep being troubled by this question of what the hell is this? Why does anybody care about these centrality measures? A nice thing about this program is that Matt's Arrow lecture is in some sense all about that. They have a new setting in which you really care about these walks, that these walk counts and which lengths you care about and how you downweight them is a notion of centrality that is relevant to certain communication processes. And then they have empirical data that shows it actually tracks how people think about their own social world broadly. So one of the things I find most rewarding about this is we had these notions that were developed often in other areas of applied mathematics where people said, okay, this is a way to measure network position, and we keep finding new ways to interpret them in economic settings. So I'm gratified by the questions of applications, and I sit tight. A lot of the talks, but especially the Arrow lecture, will, I think, provide at least provocative answers. You may not in the end believe them, but they'll give you stuff to think about. So to get back to this, the punchline of the Perron-Frobenius theorem is that there is a uniquely determined pair, eigenvalue and eigenvector, so that this equation makes sense, assuming you want a centrality measure with no negative entries. Okay, that's why I needed the
Normalizations.
right. So I can notice that once I have an eigenvector, I can scale it however I want. Right, it's still an eigenvector. So I can always assume, for example, that it sums to 1. So up to a normalization, there's a uniquely determined pair, lambda and a c, that makes this equation work. So going back to the school example, you might have thought that this notion of coolness was hopelessly recursive, right? That I'm trying to define my coolness in terms of the coolness of other people, but where do you get theirs? It turns out that it has kind of miraculously, the Perron-Frobenius theorem says there's basically only one way to solve this equation. So let me now, so these slides are online. I encourage you to look at this. And again, Meyer's book is a great source for the wisdom. He develops it really nicely, why this is true. So let me now quickly recap what we said about centrality measures so far.
Now, this was you said, are we talking now directed or undirected?
This is arbitrary. It can be directed.
Okay, So what do you do if you have two components that are connected but not strongly connected?
That's not irreducible. Oh, you want?
I know, but how would you define centrality there?
Okay, good question.
Can you repeat that?
The question is, if I have, suppose I have, so this can be weighted, directed, whatever, but it is under the assumption that the matrix is irreducible. So Sergio asks, what if I have two components, C and C prime, and I have one edge? Okay? This provides actually a good opportunity to tell you that you know this guy already. Many of you are friends with the Perron-Vector, although you may not know him by that name. It's the stationary distribution of a Markov chain, right? So if M is here I've defined it to be a right-hand eigenvector, but if M is a Markov chain, if you look at M transpose, then the Perron-Vector in this sense is just the stationary distribution of the Markov chain, okay? So that's if you understand Markov chains, that provides a rich source of intuitions about what's going on with these centrality measures. So Sergio's question is, what will happen to eigenvector centrality if we have a graph with two strongly connected components and an edge between them, so then you can see if the arrows now represent how a Markov process is traveling, right? You have states and an arrow means a transition is sometimes made from this state to this state. Then in a picture like this where there's no arrow backward, the particle will always end up here, right? If you have a particle hopping around on these states, it will eventually make its way down and it'll never make its way back. And because centrality is proportional to your station, in this interpretation, it's proportional to your weight in the stationary distribution, that means that all these guys have centrality 0. And this provides...
It's sort of a nice moving example for Bonacich centrality. Part of the reason why the Bonacich
Yeah, example what, sorry?
for the Katz-Bonacich.
Yeah.
So then it doesn't transition out and you still get non-zero and then it
Right. So with
Take B not zero.
exactly. So B not...
keep some
Yeah, because you want to have some, you don't want to put zero, you are losing information out of that.
That's why you keep the B non-zero.
Yeah, exactly. So and related to so this is why these measures that have a B in them are so Matt's point is that people like having the B in there, even if it's just a constant vector to sort of avoid bias, is valuable. Some people believe that this way of measuring centrality, just like this, was invented by the Google guys. They indeed wrote about it in a 98 paper in which they introduced PageRank. Their argument was basically we should rank web pages by their centrality in the link network, and they gave a Markov chain kind of interpretation. Question?
So then, if you take B to 0, when B approaches to 0, does it approach to eigenvector?
Yes, in a sense, yes. I'll show you that in a moment.
Even though it will never be like.
Let me
We talked about this example when they are not connected. It will not.
So yeah, with an irreducible, if you start with an irreducible one,
Yeah.
and then then for that it'll converge. Outside that, I'd have to think about it.
Okay.
So in Google, the way that just 1 second. If you look at the matrix of links on the web, that happens not to be strongly connected. That's just an empirical fact. So how did Google deal with it? They added what they called a teleportation parameter, which is that with some probability, at every step you just bounce to a uniformly at random place on the web. Okay, and it turns out, little exercise for those of you who are more familiar with this stuff, that is exactly isomorphic to adding these B's. So if you could either think about pure centrality, but on a modified graph, so pure eigenvector centrality, which is this thing, on a graph that has teleportation built in, this probability 10% you bounce to a uniformly at random spot, or you can think about a version with these B's, and the exercise is figure out how these two things are the same. But they give one, if you make the parameters correspond appropriately, they'll give you exactly the same notion of centrality. And as Matt pointed out, these are both ways of rescuing yourself from this problem where you get all these zeros that you don't want. Sergio is doing it. Okay. But I should say that this has some interpretations that make sense. So we'll come back to this when we talk about, remember that for when we talk about processes of diffusion of information or influence on networks. Sometimes the cases where the network is not strongly connected are interesting. So I have about 5 minutes, which is the right amount of time. Let me recap and go and talk about Nir's question a little bit. So I'm going to do a 2-column recap of what we saw. When this matrix, lambda inverse G, has all eigenvalues less than 1, which is equivalent to the statement that this lambda number here is bigger than the biggest eigenvalue of our matrix, then we can write a formula for the centrality like this. It's just this weighted walk count. Here, the centrality of I counts walks from Mr. I to various places weighted by the this b tilde at the arrival point, but we often make that equal to 1, so we're not introducing any other variation. And I should just point out that when you do start with the uniform vector and you use a small alpha, the ranking of nodes you'll get is just degree centrality, right? The only part of this that will contribute will be the first term, where the entry that Mr. I has is just how many links Mr. I, or his degree. So for low alpha, this picks up degree centrality. And Nir kind of suggested, with the way I'll frame his question, is it turns out that when alpha gets as high as it can be, for this still to make sense, right? So if you think about making this alpha higher and higher, this thing wants to blow up because this number of walks is, certainly not decreasing. If you make alpha as high as it will be before everything blows up, it turns out you recover eigenvector centrality, you recover page rank, this where there's no the version of this with no b's. So, when lambda actually, so that it turns out that magic place is lambda equals lambda 1. In that case, the solution has the equation has one non-negative, non-zero solution. When b tilde is 0, it's called the eigenvector centrality, which doesn't have the standard letter, unfortunately. In this lecture, I'm calling it p. And something that I'll leave you as an exercise is if you start with an irreducible graph and you let lambda descend down to lambda 1, which is the largest eigenvalue of G, the Bonacich centrality will, two things will happen. They'll blow up. They'll all become very big, okay? But the ratio of mine to yours will converge to the ratio of my eigenvector to your eigenvector centrality. And as I've mentioned, there are close connections of these activities to Markov chains, because when you have a Markov chain M, the Perron vector of its transpose is the stationary distribution. Okay, but Perron vectors are defined for more general class of matrices than Markov chains. In particular, you don't need them to be a Markov matrix. I'm sorry, you raised your hand before.
Yeah, it's just that I was thinking that could be when you have some sort of condition for reversibility, which is very useful for finding stationary vector.
Okay, so if your matrix has a reversibility property, there are very nice formulas. So 2 things to say. So the question is, if reversibility is satisfied, or some notion corresponding to the Markov chain idea of reversibility, you have nice formulas for centrality. And that is true. It turns out, so let me give another little exercise. If your matrix M has all rows summing to, so suppose you take a graph, a symmetric, an undirected graph, and then you make a matrix out of it by having everyone have one total unit of attention to give out. So you make the rows of your matrix sum to 1, but otherwise you keep the same edges as you had in the graph. So if I have 7 friends, my edges will be 1/7, 1/7, 1/7. Okay? It turns out that in that case, eigenvector centrality, this thing with b equals 0, will actually just be proportional to the number of edges you have in the original graph. Okay? That's something you can check by computation. So in some cases, these notions have easy formulas. But of course, part of the point of studying eigenvector centrality is that we think that result is a bit of a letdown, because we hope that this is picking up more of the structure of the network than just the degrees. If we cared about the degrees, we could just but there are, it's interesting to think about when you can do these computations and have explicit formulas for C. Okay, so let me quickly let me wrap up with the following slide, which sort of tries to build. I'll go quickly to leave you something to do on your own and to think about. So remember this diagonalization we did. We just to be very precise, we could do this because G is a normal matrix. It satisfies this equation. Actually, for the case we were studying, G is a symmetric matrix, so it satisfies this equation very much. Now, if I take this equation and I rewrite it, I get what I'm doing is I'm just multiplying on the right by S. Okay? On both sides, I can write G times S equals lambda times S. And if you stare at that formula for a while, actually this is wrong. It should be G times S equals S times lambda. But that says, if you think about what that matrix equation is saying, it says that a certain column of S is an eigenvector of the matrix with eigenvalue corresponding to the entry in that column of lambda. So for example, if I look at the first column of S, that's the eigenvector corresponding to lambda 1. Okay? And that eigenvector is the Perron vector. It's eigenvector centrality. So I don't have time to go through the details, although maybe some of you can read them. But you can use this to write out a formula for the walk counts. So it turns out that once you use this little bit of algebra, you can write that the number of walks from Mr. I to Mr. J is approximately of length L is approximately proportional to lambda 1 to the Lth power, okay, times Pi times Pj. So Pi and Pj, which are the Perron vector entries for Mr. I and Mr. J, that's what determines the number of walks they have. And if I add up across all people, since I can always normalize the Perron vector equal to 1, the total number of very long paths going through me is just proportional to my Perron centrality. So that's a way of saying that as you take alpha really high, so it's basically the high terms of that series that dominate, that'll just be picking up eigenvector centrality. So again, the point is to give you some sort of, to whet your appetite a little bit. You can now go read about this stuff. You will be meeting these people, especially in these various notions of centrality in Matt's lecture, on gossip and in lots of other places. And lastly, thank you so much to the organizers. I'm super excited to be here, and I hope everyone enjoys the summer school.